we notice, and we need this image for two things. First, we need the header information to do the memory mapping and find out where in memory stuff actually is, because the core dump doesn't tell us. And we can also just go ahead and compare the things that really shouldn't change, like code. Code should actually not change in runtime. If it does, something really bad happened. So this is what we do. We take the header information and map it out on the core, and then we can directly compare code segment and read-only data, which allowed us to detect the first publicly disclosed rootkit. Topo from Core Security wrote a iOS rootkit, and he called it Dick. So we could actually see where it is, and he provided us with a patched iOS version, so we could actually test our code, because it's kind of boring to write a forensics tool and always try to detect your own chain codes. So it was interesting to see how we performed against others, and it worked quite well. So we can tell you that Topo's Dick is exactly 3 times 4. Now, essentially, those are the 3 places where he patches the iOS image. What he does is the classic thing of patching the functions that tell you if passwords matched or not, to always return 1. So once you have that information, you can actually take the core file, load it into IDA, and just don't disassemble anything except for go to this virtual address and press C, and the only thing that comes out of it is the rootkit. And everything that's still data is not the rootkit. So it's really easy and useful. If anyone wants to see the full report, in SIR Online, there's a case number that you can enter, and then you see the case. Yeah, I hang around way too much with Rudy, so I use long hashes. But that's my fault. So what we also do is we take this memory dump and reconstruct the entire heap, because the heap contains a lot of metadata. What's cool about this is, because they all share one heap, what they do is they go and write on every heap block a string that actually says what this heap block is used for. And pretty much like if you're living with other people, you label the stuff in a fridge. That's what they do, so they can blame each other. If someone overflowed his buffer, they can say, it was your heap block that spilled into mine. This is really useful for the forensics approach, because we now know what each heap block is and what it is supposed to do. The problem is, once you start analyzing something like this, you base it on the assumption that, well, they have a common heap, it's a double linked list, they will not go anywhere else, and it will be integrity checked, and it will be fine. Wrong. People have very interesting ideas, like this. I have the firmware for the ISDN line card of my router in the read-only memory, in the read-only data section of my program. Now, since I applied the firmware after booting, I don't need this memory anymore. So what I'm going to do, I'm going to free it by linking the read-only data section block that I just used into the heap. Which is great if your idea of an integrity check was, hey, let's first check if this memory that the heap pointer points to is actually in the heap area, because if it's not, then it is very much looking like one of the heap overflows I've wrote. Well, here goes the check. So we ended up having most of the functionality or full functionality of the process called check heaps, which is the onboard integrity checking process on iOS. And we can find holds and stuff, yeah, essentially integrity check this heap. We also get the process list out, which also lives in the heap. And we can now go ahead and create individual stack traces for the individual processes, what iOS itself cannot do. Like when the box is popped, you don't see which process actually got taken over, because it's all one memory area. You can write anywhere, and you can easily jump from one process to another without even noticing as an attacker. So we needed individual stack traces to actually find stack overflows. And we find things like TCL backdoors. People use Tickle backdoors for quite a while, especially if they used to work for an ISP and now don't. Because people tend to like their level of access that they have, and they tend to want to keep it. So Tcl scripts are the tools of trade for network administrators to have access to their routers. They're very short scripts that essentially bind to a port, take the string that's coming in, put it into the shell, get a response out, send it back. Right now we're just dumping out the text from the Tcl scripts because I have no idea how much I need to drink before I will start writing a Tcl decompiler for the compiled stuff. Then there's this interesting thing about the iOS packet memory. So iOS forwards packets in many different ways. The slowest is process switching, which really goes to the CPU, and then there is like fast switching and particle systems, and then you have special hardware and whatnot. And at least all the access layer stuff uses I/O memory, which is carved out from the main memory. So you get actually core dumps individual for the I/O memory, which is cool because it contains ring buffers. The ring buffers are by size, you know, like T-shirts, like small, medium, large, extra large, tent. And this is and this is what they do for packets. So if your network handles big packets all the time, like regular full TCP packets for downloading porn, then they end up in a different ring buffer than the small ones, like pings. So that means newer traffic doesn't actually erase older traffic in a linear way, but in a environment-dependent way. And they really try hard to not copy packets around in memory because that's slow. You actually find a lot of stuff. So what we can do is we can take the information that we have from the heap reconstruction, go to the I/O memory, and dump out the packets, which is useful because then you get a PCAP file. This was just captured from this box sitting in our office, so you see Windows blah blah talking. And you can turn all the traffic that went through this router in the recent past into a PCAP file. That is very useful because potentially if the box crashed because of the iOS exploit not working, it was caused by a packet coming in. Very rare case for a router. And this means since you're still holding all the pointers, you can find the pointers on the stacks of the process pointing to the packet, which means fuzzing now became really easy because you're just throwing shit at it, and when it crashes, you go like, give me that one packet that crashed you. So that is useful. And it can also like disclose information on, let's say you have a box that's sitting on an individual interface of a router, because the individual interfaces also have ring buffers. So if this box is sitting alone there and it's not too shady, then there's a long traffic history. And if this box got popped and let's say RM'd and like it's just empty, you can still go to the router and unplug it from the network, not from the power, and get the packets out, and then potentially see what popped the machine or who talked to it lately. So coming to the challenges. The challenge with iOS on both sides is the combinatory explosion of platforms, aka Metal, iOS version, major version, minor version, release, special release, feature set, and additional hardware stuff that you can put into. So essentially, in production networks today, you're looking at over 100,000 different iOS images. Now, when you keep in mind that this behaves like a single program, and you probably realize that if you ever compiled your program and looked at it in your debugger, and then you changed a line in your program and compiled it again and looked in your debugger, it actually looked a lot different because all the stuff got moved. Now this applies to the entire memory space here. So you can't actually say where stuff is in memory. Even the stacks that, for example, on Windows exploitation or Unix exploitation, before address space layout randomization, you knew exactly in which address range the stack is, and then you just put an obsolete on it and then execute your code. With iOS, you can't do that because The stacks are blocks in a heap. The heap is actually on top of the data segment and is defined by the end of the data segment. So you would need to know how big the data segment is, and you would need to know how big the code segment is, otherwise you don't know where your stacks is to be expected, and then it's in the heap, so it's entirely unpredictable. This is really a great headache because we actually have to jump through many, many loops to get the address information out when we get a core file into SIR. But it's also a big headache for iOS exploit writers, which is why getting stable exploits is so expensive and hard to do. Yeah, this is what I just said, because remotely, you also have this 1 in 100,000 chance to figure out what iOS image am I attacking. And all the exploits so far had fixed addresses that they jumped to. And also, any exception that you cause, anything that doesn't work in your exploit, reboots the router. Which is shitty because on the Unix side, for example, there was exploits that brute forced because the server respawned over inetd, and so you could brute force the address. Well, with the router, you can't do that because the people in the network management center may be lame, but if this box is blinking red for half a day, they will probably notice, and half a day gives you about, what, 20, 30 attempts. So that probably doesn't hold. Yeah, I already mentioned that all the exploits published so far are for one fixed image with one specific feature set. So essentially, the fact that the iOS coders actually recompile this entire crappy thing, and yeah, there's a reason why iOS actually shows the name of the guy who compiled it when it boots, because everyone has apparently their own makefile, because the thing looks different if A or B just compiled the same image, which is why they have so many image versions. So their messed up build process is actually their best protection right now. This is what it comes down to. Because it is very similar to the source port randomization patch that everyone applied because Dan couldn't keep his mouth shut. So performing research in this area is crucial because it has always been on the open research side, has always been an issue that you couldn't really discuss shellcodes. I mean, people give talks on iOS shellcodes, but then they're iOS image codes because they only work for one image and they don't have stable code execution, so what are you going to do with your shellcode? So this was always a big issue, so we actually spent about a bit time there to understand how the forensic side will actually look if we have stable code execution. So this is the question, where to turn to. If I overwrite the link register, the saved link register on the stack, we're talking PowerPC here, and return, I need to specify an address. And I can't be vague. I can't tell it to just jump near my code or something. So when we look at the memory layout, there is not much we can turn to. The first idea I had was jumping into I/O memory. That makes most sense because you're trying to execute the stuff that you send in with your packet, right? Oh, yes, so good. So we fumbled around a while, and we actually got it to work that we had an IPv4 packet that was valid and executable PowerPC code. Until I found out that the I/O memory is not executable. Should have checked that first. But the packet is cool. So in my desperate search for a place to jump to, I found the ROMmon code. Remember this BIOS thing that boots the device? This code stays in memory, and it stays at a predictable address. And it's not used by iOS. And the version distribution is a lot smaller. So because it gets shipped with the device, hence the name ROM. People can't update it. That's good. That is useful. So a quick search revealed that this is ROM1 versions for the 2600. You see there are 8 entirely, like there are not more than 8, and their shipping time